Section 6.2, Properties of Power Series. So a really useful idea is that if we know the power series representation for one function, we can use it to write the representation for other related functions. This is related to the idea of limits, how if we can take the limit, if two limits converge, we can sum the two expressions to get and sum the limits. Same idea here. If we have two power series, we can sum or take the difference, and we can just sum what they converge to or take the difference of those. That's useful if they converge to those functions respectively on a common interval, wherever they overlap. Okay. Part B here, we can take a series if we have something multiplied by it. Okay, it converges to a related function there, b times x to the m, f of x on that same interval. And then if we compose, in this case, a bx to the m in there, then as long as that term is inside that interval, that's good. So let's go ahead and look at some application of that. Suppose that this first power series has an interval of convergence of -1, 1, and the second power series has an interval of convergence of -2 to 2. The question is, where does the sum, what is its interval of convergence? Well, we said earlier in part A, they have to have a common interval. Well, the common interval here is -1 to 1. So that is the interval of convergence of the sum. Now the second one has to do with a composition. First, let's write this n equals 0 to infinity of an of 3x to the n. Our composition here, the bx to the m there, is 3x. So as long as bx to the m is in the interval -1 to 1, then we're in good shape. So what we need to check then is that the absolute value of 3x is less than 1. Well, that occurs when the absolute value of x is less than 1/3. All right. So that would mean our interval, well, first our radius is 1/3, which means our interval is -1/3 to +1/3. Since that's what we were asked for, that is what we want there. Example 2, suppose an x to the n is a power series whose interval of convergence is -1 to 1. Find the interval of convergence of an x over 2 to the n. Okay, it's the same idea as part B there. We want to make sure that x over 2, the absolute value of x over 2, is less than 1, because here we have to stay in that interval. Well, that would be true when absolute value of x is less than 2. So therefore, our interval of convergence is -2 to 2. For our next example, we want to recall that 1 over 1 minus x, the sum of x to the n from 0 to infinity, those two functions are identical. Okay, so that is going to help us out on this next one, because we want to construct a power series for f of x equals 3x over 1 plus x squared. So let's see if we can write it in the form 1 over 1 minus x. All right, let's first factor out a 3x. Let's factor out a 3x, and that would be 1 over 1 plus x squared. Well, we really would like a 1 minus something there. So let's change this. Let's move all of that. Make that 1 minus -x squared. All right, that is of that form, so this will be 3x times the series from 0 to infinity of -x squared to the n. Okay, now that is valid. What I just did, that is valid as long as absolute value of -x squared is less than 1, which is equivalent to the absolute value of x is less than 1. Alright, so everything I do further is good as long as the absolute value of x is less than 1. So that's the series from 0 to infinity of negative 1 to the, go ahead and make that negative 3 to the n of x to the 2n plus 1. Again, as long as the absolute value of x is less than 1, that is the power series representation for f of x. Okay, part B. Construct a power series for f of x equals 1 over x minus 1 times x minus 3. Alright, so to begin with, let's see if we want this in 1 over 1 minus x form, like we had the others. So let's see if we can work out a partial fraction decomposition. All right, that would indicate that 1 equals a times x minus 3 plus b times x minus 1. And for x equals 3, that would mean b is 1/2. And for x equals 1, evaluating that, here, let me just add that intermediate step there. That is 1 equals, and the first term, the a term, is 0. So b times 2, so b equals 1/2. Evaluating x equals 1, I get 1 equals negative 2a, and the b term is 0. So a equals negative 1/2. So I'm going to write f of x as, my a term is negative 1/2 over x minus 1 plus 1/2 over x minus 3. Alright, now we want to have it in the 1 over 1 minus x. Remember, that's kind of our goal, is to have something that looks like that, because that is equal to that series x to the n for absolute value of x less than 1. That is our goal. So let's make this 1/2, factoring out a negative 1. Okay, that will be 1 minus x. Alright, minus 1/2 over 3 minus x. Alright, now factoring out the 1/2, go ahead and do that real quick. If I put this 1/2 and this 1/2 out here, if I put that in there, 1/2, let's factor this just a bit more. This will be 1/2 times the sum n equals 0 to infinity of x to the n minus 1/2, and I'm going to take out a 3 as well. Let me continue a little bit of scratch work here. This one, this right here, is 1/2. And if we take out a 3 as well, that'll be 1/6 times 1 over 1 minus x over 3. So this will be minus 1/6 n equals 0 to infinity of x over 3 to the n. Now, this is valid as long as the absolute value of x is less than 1 and the absolute value of x over 3 is less than 1. That would mean absolute value of x is less than 1 and it's less than 3. Therefore, this is only valid whenever absolute value of x is less than 1. That's the common interval there. Now we can write this as one power series. Make this sum equals 0 to infinity of 1/2 minus 1/6. Let's go ahead and put that as 1 over 6 times 3 to the n of x to the n. And again, that is for absolute value of x less than 1. So that makes our interval of convergence -1 to 1. We have not tested the endpoints, but we know that it will be valid from -1 to 1. Construct a power series for this function. Okay, the same rules will apply here. Let's manipulate this so that actually we don't need that yet, so that it is two separate 1 over 1 minus x, that form. All right, so using partial fraction decomposition. All right, and let's clear fractions. So 1 is a times x minus 2 plus b times 1 minus x. For x equals 1, that is 1 equals negative a. A is negative 1. And x equals 2. 1 equals negative b. So b is negative 1. Now I am going to go ahead and flip this, so I'm going to write f of x equals negative 1 over 1 minus x plus 1 over 2 minus x. Let's factor some things. That is negative 1 times 1 over 1 minus x plus 1/2 times 1 over 1 minus x over 2. Now I can write a power series for that. Negative sum of x to the n plus 1/2 sum from 0 to infinity of x over 2 to the n, as long as the absolute value of x is less than 1 and the absolute value of x over 2 is less than 1. Well, this is the absolute value of x is less than 2. So this is only valid as long as we are less than 1. So absolute value of x is less than 1. So let's go ahead and combine these two. This will be the sum, n equals 0 to infinity, of negative 1 plus 1 over 2 to the n plus 1 x to the n for absolute value of x less than 1. So our interval of convergence, we'll go ahead and say what that is. Interval of convergence is negative 1 to 1 again. So there's our power series representation in that given interval. All right, example 5. Find the function represented by this series, and then find the interval of convergence. Okay, well, let's see if we can, we're going in the opposite direction. Let's see, we could write this as 2x to the n, which, as long as absolute value of 2x is less than 1, is equal to 1 over 1 minus 2x. Well, that would imply absolute value of x is less than 1/2. So there's our function. There's our function. And our interval of convergence is negative 1/2 to 1/2. Now, I want to go ahead and test the endpoints with this one. Okay, if I had x equals negative 1/2, if I had x equals negative 1/2, if I evaluate that in this series, that would be 2n times negative 1/2 to the n, which is equivalent to the alternating series, which diverges. And if I evaluate this at positive 1/2, that is 2 to the n times 1/2 to the n, which is equivalent to the sum of 1. It's 1 to the n, that also diverges. So this interval of convergence is as good as it gets. Number 6, find the function represented by this power series, 1 over 3 to the n times x to the n, and find the interval of convergence. Alright, well, based on our geometric ideas here, we can write this as sum from 0 to infinity of x over 3 to the n. And this is valid as long as the absolute value of x over 3 is less than 1, which would mean the absolute value of x is less than 3. So there we have our power series. So let's write this as a function that is 1 over 1 minus x cubed, 1 over 1 minus x over 3, which if we multiply through by 3, that's 3 over 3 minus x, with absolute value of x less than 3. So there's our function, and our interval of convergence. Interval of convergence is -3 to 3. Now, for the same reasoning as that last one, I'm not going to redo this, but for the same reasoning as this last one, if I evaluate the endpoints at -3, I get the alternating series, which diverges, and at evaluating this at +3, I get the sum of 1, which also diverges. So my interval of convergence is, in fact, just -3 to 3. All right, find the function represented by this power series. All right, now this one is a little bit different, mostly because the ends begins at 1, not 0. All right, so the idea of a geometric series is the first term, okay, the first term divided by 1 minus the ratio. Okay, so far our first term has always been 1, so it's been of this form. So we'll want to put our first term there. So let's go ahead and write this as our first term. It's already set up as a geometric series. So the first term would be n equals 1, which would be 1 over x minus 6. That's our first term. Now the common ratio, so here's each of my terms. So the second term is 1 over x minus 6 to the 3, 1 over x minus 6 to the 5. So my ratio is 1 over x minus 6 squared. So there's my function. Now this is valid as long as the absolute value of 1 over x minus 6 squared is less than 1. We'll revisit that in a second. So let's multiply through by x minus 6 squared, x minus 6 squared. Get a nicer looking function there. That will be x minus 6 over x minus 6 squared minus 1. Alright, now let's revisit that interval there. This interval is only true if x minus 6 squared, the absolute value there, is greater than 1. Taking the square root, because I can do that, absolute value of x minus 6 is greater than 1. And this is the same as saying x minus 6 is greater than 1, or x minus 6 is less than -1. So x is greater than 7, or x is less than 5. So our interval of convergence is -infinity to 5 union 7 to infinity. I believe this is the only time we're going to have this, and the only time we've had this so far. But this function is only valid as long as you are less than 5 or greater than 7. It has to do with the reciprocal why it does that. So be on the lookout for weird things that can happen. All right, number 8. Suppose you win the lottery and are given the following 3 options. 1. Receive $20 million today. 2. Receive $1.5 million per year over the next 20 years. Or 3, receive $1 million per year indefinitely, being passed on to your heirs. Which is the best deal, assuming the annual interest rate is 5%? We can answer this by working through a series of questions. So, number 1, how much is the $1.5 million received annually over the course of 20 years worth? Okay, assuming we have an annual interest rate of 5%. Well, the year 1 amount, the payment 1, would be the payment 1 times 1.05 to the 1, and it's the $1.5 million. Okay, so the current value, based on the interest rate there, the current value of that is 1.5 million divided by 1.05. That is how much it's worth as its present value. Year 2, well, that would be the present value of that is 1.5 or 1.05 squared, because that interest is accumulated over 2 years at that point, which would and equals the 1.5 million, which means that P2 is 1.5 or 1.05 squared. All right, so the value over those 20 years, it continues in that way, would be 1.5 over 1.05 plus 1.5 over 1.05 squared plus all the way up to 1.5 over 1.05 to the 19, 1.5 or 1.05 to the 20. So the present value at this point, given the interest rate of 5%, is the sum of all of this, which is $18.693 million. Okay, so that's how much it's worth over the course of the 20 years, getting 1.5 million each year. Okay, so let's see if we can make this a little more generic. 1.5 was our amount received each year, and the 1.05 was 1 plus our rate. So each of these values, each year, the amount that it's presently worth is C divided by 1 plus R, which means the amount, the present value over the course of n years is C over 1 plus R plus C over 1 plus R squared plus C over 1 plus R cubed plus indefinitely up until C over 1 plus R to the n. It'll be a partial sum over n terms. Alright, so find a formula if, for the present value, if annual payments of C dollars continue indefinitely. Well, that would be part B, but infinite. Alright, so that would mean the limit as n goes to infinity of Pn, that would be the sum from 1, let's go ahead and start that at 0 to infinity, of C over 1 plus R to the n plus 1. Now we really want a formula that we can evaluate in, okay, given the C dollars and the interest rate. So let's factor C over 1 plus R out. Okay, and that is 1 over 1 plus R to the n, in which we can write that with the exponent on all of that. Okay. So, as long as the absolute value of 1 plus 1 over R is less than 1, this is equal to C over 1 plus R times 1 over 1 minus 1 over 1 plus R. little bit of algebra, clearing the fractions there mostly. C over 1 plus r times 1 plus r over r. So our formula is C over r. So the present value of all of it is C divided by r. Alright, so now let's use that formula for this next part. Find the present value of $1 million paid annually indefinitely. Well, our interest rate is $1 million divided by 0.05 would be $20 million. $20 million. Now we want to compare these values. So in part A, we had 18.693 million. In part D, we have 20 million. And then there was the lump sum. So obviously, either of these two options would be equal and the better of the choices. Okay, moving on, multiplying power series. Now I suggest you read this and try to figure out what's going on here, but the idea here is something called a Cauchy product, which is, for all intents and purposes, infinite distribution, okay? What we're going to do is we're going to have two infinite series. We're going to multiply them term by term. So in this example we're multiplying 1 over 1 minus x times 1 over 1 minus x squared to come up with the power series for 1 over 1 minus x times 1 minus x squared on the interval -1 to 1. Alright, so 1 over 1 minus x is 1 plus x squared plus x cubed plus, and 1 over 1 minus x squared is 1 plus x squared plus x to the 4th plus x to the 6th, continuing indefinitely. So what we are going to do is distribute. Lots of distributing. This is 1 times 1 plus x squared plus x to the 4th plus x to the 6th plus x times 1 plus x squared plus x to the 4th plus x to the 6th plus ... plus x squared times x times 1 plus x squared plus x to the 4th plus x to the 6th plus, and we continue. Now, if we do a little bit of combining like terms, what you'll notice is there's only going to be one constant term. It's from the very first one. There'll be one constant term, a 1. There's only one x term. There's only 2 ways to get an x squared, 2 ways to get an x cubed, 3 ways to get an x to the 4th, 3 ways to get an x to the 5th, and that sort of pattern just continues on as long as the absolute value of x is less than 1 because of our interval of convergence right here. Because that's the common interval for these two as well. All right, number 10, I'm going to go in reverse. Here I have an infinite series and I want to find a rational function from this. So I'm going to do a little bit of infinite factoring. Infinite factoring. So I'm going to group these terms here by powers of 4 minus 1, 4 minus 2, and 4 minus 3. So my powers of 4 are these. So I have negative x to the 4th minus x to the 8th minus x to the 12 minus, continuing on, all right, x to the 4 minus 1, so this will be an x cubed, minus x to the 7 minus x to the 11. Okay. Next down, x squared, x to the 6. These are all adding. X x to the 10, and then I have x plus x to the 5th plus x to the 9. All right, now I'm going to factor each of these. Now notice that what we are given there is the sum of all four of these. Okay, I've rearranged them because I know it's going to converge to a function. All right, so now if I factor that out, I'm going to take an x to the 4th out of this first one, which is 1 plus x squared plus, or x to the 4th there. All right, x to the 8. Yeah, there we go. Okay, now the next one I'll take out a negative x cubed, which will be 1 plus x to the 4th plus x to the 8. Next one I'll take an x squared out. That's in common with all of them. 1 plus x to the 4th plus x to the 8. And hopefully you notice we are having something very nice happen. Once we factor that, we have the same thing on all of them. Now, this section right here is geometric. It's geometric. And the sum, well, the ratio is x to the 4th. So the sum of this part right here, if I take it out, all right, is, oh, if I'm just going, this is already a sum. If I take the sum, that is 1 over 1 minus x to the 4th. Plus this part that I have factored out, negative x to the 4th minus x cubed plus x squared plus x. All right. That is a sum of all of these. Okay, of 1, see that is x to the 4th to the n is what that is. Okay. So that means our rational function here is negative x to the 4th minus x cubed plus x squared plus x over 1 minus x to the 4th.